Hey everyone, so who wants to get rich quick? Everyone knows that all the cool kids are getting into peer-to-peer these days to make fat stacks of cash, right? No? Everyone's getting in on the action. Haven't you heard? Floyd Mayweather is a boxer and he has an ICO and a token. So does Paris Hilton. I think we should make a virtual internet money ICO token cryptocurrency thingy right here at Nordic.js 2017. Maybe it can be, yeah. Maybe JavaScript themed in some way, like ECMA coin or BitScript. I don't know, I would use something named BitScript. Actually, the truth is I know nothing about cryptocurrencies, and I do think what's going on right now in that space is pretty incredible though. But that's not the kind of peer-to-peer that we're going to talk about today. The kind of peer-to-peer that I know about involves significantly less money for me, but also significantly less fraud. So don't be disappointed. We'll have lots of demos. You won't get rich, but I promise it'll be great. So let me tell you a story. Once upon a time, it was 1962. Global nuclear war seemed imminent. The US and the USSR were embroiled in the Cuban Missile Crisis, pointing hair-trigger missile systems directly at each other. We were poised on the brink of World War III. US leaders were worried about fragile communication networks that would break if only a single critical node was taken out. They needed a communication network that could route around failure, so a single unavailable node wouldn't cripple the whole network. And thus the internet was born. Little did the creators know that just a few decades later, 95% of internet traffic would be comprised of cat GIFs and animal-based memes. You know, you don't have a real JavaScript talk unless you have at least 3 cat GIFs. So it's in the rules. I know, I've read them. So now we got that out of the way. We can proceed. The internet actually, so it ended up having 4 properties that were interesting, I think. So the first is resilience. So the internet routes around failure when possible. And this was so that if like 1/2 of the US were destroyed, in a nuclear attack, the other half would at least be able to communicate with each other and coordinate a counterattack. We also have no middlemen. So middlemen are single points of failure. So we can't have those. There could be no sort of chain of command or rigid hierarchy in the design of the net. That would be no good. And so as a result of this disintermediation, anyone could actually just connect to the network. Well, at first it was just universities and governments, but eventually it opened up to commercial use, and anyone could just show up, plug in their server, and make a service available to the network. And users could get online by just signing up with an ISP and getting connected. So compared with other mediums like TV, the internet was extremely democratic and open, and it goes without saying, we all come together and make the internet this weird, amazing place. So these 4 properties were critical to the success of the internet, and interestingly, they're also critical to what people usually think of when they hear the term peer-to-peer. When people say peer-to-peer, they think of these 4 properties. But the thing is, peer-to-peer apps and protocols are actually built on top of the internet, right? So the internet is already peer-to-peer. The internet already has these properties, so what exactly distinguishes a peer-to-peer app? When we say peer-to-peer app, what distinguishes that from just a normal internet app or a web app, right? So I was thinking about this, and the best explanation I have is for this sort of terminology confusion is that in the early days of the internet, it looked sort of like this, where you had lots of different services to choose from. No one service was too powerful. So this is like representing, users connecting to different services. But as the internet has grown, and so-called network effects have made it so that a few services have come to dominate the rest. So today the internet looks more like this. A few services where users spend all their time and all of their energy. So that's fine, right? I mean, users are free to use whatever service they want. If they don't like this one, they can use that one. And so it's all good, right? Well, the thing is that we should ask ourselves how this new network topology changes the properties of the internet. So nothing has actually changed about how IP addresses work or how TCP/IP works. But if the network now looks like this, is the internet still resilient in the ways that we talked about before? So I think the answer is yes and no. We have a lot more experience building reliable large-scale systems, so that's a form of resilience, but they're pretty much all run by a few companies. So when AWS had an outage earlier this year, half the internet just stopped working. So next question, is the internet still free of middlemen? So not so much, unfortunately. Take like email as an example. In the past, you might get your email from a local internet service provider or your university or your employer. So if I go to send you an email, I would connect, my email app would connect to your email server and send the message via a direct connection like that. You might even be running your own email server. So I literally might be connecting to a computer in your house to send you an email. But now Google runs everyone's email, and even the email of large universities and companies, and there aren't as many local ISPs anymore, at least in the United States. There's just a few big ones. And so the consequences of this haven't been good. So, Gmail is really good at filtering spam, but more broadly speaking, instead of having hundreds of thousands of different independent organizations deciding which types of usage they want to allow what types of usage they want to allow on their services, we now have a one-size-fits-all approach where just a few companies are making decisions that affect all of us. So this is an example where Facebook decided to deactivate an account of a mother because she posted a breastfeeding picture. Totally they're right, but in a more diverse ecosystem, we would have people making different decisions about these kinds of things, and it wouldn't be this one decision, live with it, you have no other choices. They ended up relenting in this case and changing their policy, but the point still stands. So next question, is the internet still diverse? So yes and no, we have lots more people connected, so that's good, but the decisions of single companies in single countries are determining what we see online. So one company's cultural values and business motives can often stifle minority views. So this example, LGBT videos were hidden by YouTube for unknown reasons, probably business related. And then last question, is the internet still people powered? The modern internet is actually really people-powered in that nearly everyone is involved in contributing to it in some way and producing all the content that we have on the internet. But people-powered is different than people-controlled, which is what I think that's really getting at when we talk about people-powered. And this is mostly because of the client-server model that the web forces on us. So all user data is usually stored on remote servers that have all the power in this relationship, and they're not stored on the user's devices themselves. So this means that if a company wants to change and make changes that are for the worse, there's no way for you to opt out. So as one example, this is Twitter. In the past, they decided to add advertisements and switch to an algorithmic feed and banned third-party clients, all decisions that users were upset with, but users had no way to opt out. Okay, so quick diversion. I haven't introduced myself yet, so I'm Feross. You might know me from WebTorrent, a torrent app that works in the browser, and also Standard.js, which is an opinionated JavaScript linter that doesn't allow any configuration at all. Yes? Thanks. The goal was to end bike shedding in teams, and quick show of hands, how many people use Standard here? Oh, cool, wow. How many have heard of it? Okay, nice. Yeah, so people got really mad when I published Standard. It's pretty funny, I think, because it was designed to end bike shedding and code style discussions, but I ended up leading to tons more discussions like that, for me at least. The upside is I deal with the bike shedders so that you can focus on getting things done. So if you really end up adopting Standard, what you're really doing is outsourcing all of your team's code style arguments to me, and I deal with them for you. You're welcome. Anyway, thanks. So at the moment, I'm working on a new site called NodeFoo, which is going to be a code snippet sharing website. It's not finished yet, but I thought I would just mention it because I think it's going to be cool. And it was inspired by this Twitter poll that I made where I was like trying to figure out how to make the node docs better because people always complain about them. And the number one thing people wanted more of was more examples. So I basically want to crowdsource the creation of all of those examples so that we can put them back in the node docs. And so I've been actually live coding this site just because I thought that would be a fun thing to try. So if you want, you can follow along when I'm live streaming working on that site. Anyway, back to peer-to-peer. So I initially got interested in peer-to-peer after reading some academic papers about how it reduced hosting costs for Spotify by 88% when Spotify adopted peer-to-peer. So that inspired me to build a product called PeerCDN, which I wanted to basically, the idea was make the same technology accessible to websites so that they could get the same benefits, the same bandwidth savings and so on. So eventually I came to learn about other reasons that people use peer-to-peer besides just these examples here where you see people using peer-to-peer to save money basically in the way that they do their infrastructure. The other big reason is of course resilience, because if you want to make applications that are resistant to censorship or single points of failure or that provide some level of privacy that the web doesn't offer, you're going to need to look at different architecture entirely, right? And one of the things you'll notice about all these apps that I have up here is that none of them actually work on the web at all. Well, okay, except for WebTorrent. But the thing is that the web really didn't do peer-to-peer for a long time. And mainly the reason is because of fundamental early design decisions that enshrined this client-server model in the web at a very fundamental core level. So you have things like domains, DNS, and URLs, and there's more things that all contribute to this hierarchy and points of control in the system. I mean, just something innocuous like a URL. Like, you wouldn't think a URL is like a problem. URLs are awesome. But the thing is that the L in URL stands for location. And that means that since you're referring to the content that you want to get by its location instead of by the content itself, that means that even if the content exists somewhere in the world on someone's computer, if it disappears from the location that you know about it, then you get a 404 not found error, and there's no way for you to find somebody who has the content. So it's very fragile in that way. Anyway, I don't want to get too much into it, but it's starting to change. There's WebRTC that came out, I don't know, 5-6 years ago at this point. And it doesn't really solve all the problems that we discussed earlier with sort of the design of the web, but it does allow us to at least develop new peer-to-peer protocols that can run in the browser within existing websites. So you'll still be getting, you can design something where you'll still be getting the website from by typing in a domain name, and going to a server. But then once you get the JavaScript running in your browser, then you can actually do completely peer-to-peer stuff from that point on and not rely on the server anymore. And there's even cooler things you can do where you can just cache the app with a service worker and make it so that even if the server goes away, you can still do stuff. So just a quick update for those of you who are have been following along with WebRTC development. In 2017 now, we're approaching 100% browser support, which is pretty cool. So iOS 11 is going to have it, and Safari on desktop is going to have it now. And the only thing that's missing still is Microsoft Edge doesn't support the data channel, which is the way that you can send arbitrary text and binary data between peers. Edge only supports the video and voice features in WebRTC. But that's going to change hopefully soon. So we use the data channel part of WebRTC, which, like I said, is a way to do to send whatever data you want back and forth between peers to build WebTorrent. And so just think of data channel like a WebSocket, but instead of connecting a client to a server, it's connecting a client to a client. And so this is the part where I just briefly show you an example involving WebTorrent, which is gonna be cool. And now we're at the demos part of the talk too, which is great because we're gonna do 4 demos in 15 minutes, so get ready. Buckle up. Okay. So, nice. Is this good? Yeah, we're good. Okay. So what I have here is just a simple code pen, and I've pre-filled in a magnet link here that is in a variable called torrent ID, and I make a new WebTorrent client, and I'm just really quickly just going to download this torrent and stream its contents to a browser. So we do client.add torrent ID, make a function. So this function will get called once the torrent client has gone out to the network, connected to some peers, and figured out what the metadata is for that torrent. So that's like the name of the torrent, the list of files, and the size of each file, and so on and so forth. So this will get called when we have that. And then I want to make a variable called file that I'm going to go into the torrent list of files and get the 5th file, which I happen to know is actually the video that I want, and I'm going to append it to, and I pass in a DOM node here, but I'm just going to use a string, which will have it actually go and do a CSS selector to find the content. And so just like that, we have torrent content playing back in the browser. Thank you. Cool. Oh, oops. Don't look at that. So, with just a couple lines of code, we were able to download files with WebTorrent. So let's do another demo. So let's build a community file drop site. So the idea behind this is I want to make a site where we can we all go to the same URL, and we're all on the same page. And whoever drops, people can drop files onto the page, and then everyone else who's on the site will see that. So it's kind of like a shared whiteboard or something. So let's do a little bit of code up here in the slides, and then we'll show it the demo working at the end. Okay, so we saw how to download things with WebTorrent, but this is how we share files. So we want to be able to actually take some file data that we've received from being, the user dropping it on the browser, and we want to create a new torrent out of that and then make it available to anyone who asks for it. And so we use a module called drag drop to add a listener for the drop event on the browser. And then when the user drops something on the page, we get this callback that gives us the list of files. And then we call client.seed, which creates a torrent and then starts seeding it. And then we get this callback when that's finished. And then we pull the magnet URI property off the torrent, which tells us how to identify it. Okay, great. So now we have that. So one user is now sharing some stuff. But how do the other users on the page figure out which people are sharing things so they know what to download? We need a way for the peers to discover which torrents are available. So there's a cool module that helps with this. Just does like basically simple PubSub, but it's really useful for building demos like this. And so here's what we're going to do. We just import Signal Hub, and then we create a new instance. So this is running in the browser, and so we need to give a name to the kind of event or app that we're subscribing to. So we'll just call it demo here, and then we specify the URL of a server, which is a PubSub server basically. And so we get these two methods here. One is broadcast, and the other is subscribe. So if we call broadcast, we can send some data out to anyone who's listening to a specific channel. And then this is how you listen to a channel. You just subscribe to it, and then you get back a node stream. You can listen to the data event and get the messages. Does that make sense so far? Pretty simple, right? Okay, cool. So now we're going to combine that with the WebTorrent examples from before. So when the user drops something on the page, we take the files, and actually we're just going to take the first file to keep it simple. So if the user drops 4 files, we're just going to share the first that they dragged in, just to keep it simple. So we seed that, and then we broadcast on this torrent channel that we've created, the identifier of the torrent, and then we go ahead and add it to the page. so that we can see what we just dropped on the page. And then those who are interested in finding out about these torrents will subscribe to the torrent and add any torrents that they receive on that subscription. So that's going to go ahead and download them, and then again add them to the page with that append to method. So just a quick note about the append to method. What that does is it actually streams the content into the DOM node. So it'll actually play back the video progressively as it fetches bits of it, and that uses the media source API for that. Anyway, so let's actually do this. So I actually already deployed this to a server, and I bought a domain for the occasion, Nordic.js.fun. And so if you have your laptop nearby, go ahead and take that out and visit Nordic.js.fun, and we'll see if this works. So here we go. I'm on Nordic.js.fun, and I'm going to try dragging a picture on. So if you visit that URL, just go ahead and drag some stuff. Whoa, look, we already have 8 peers. That's cool. 6 peers. So if you drop files onto the page, they should show up here. And keep in mind, there's a code of conduct at this conference, so be careful what you drop. Oh wow, there's 25 people sharing that top file. Let's see, I wonder if the Wi-Fi will be able to handle this. Okay, I like these file names. They're good file names so far. Where's the content though? Was that someone's laptop? All right, this is unfortunately not loading on my computer. Has it loaded? Has any files loaded for anyone in the audience yet? No. Okay, I'm just going to blame it on the Wi-Fi. Here, you know what? Actually, let's try this. I'll try another tab on my computer, and I'll try dragging something on and just seeing if that. I think we're just overloaded. Oh, okay, something loaded. What the heck? I'm guessing that's like an asset for a game or something? I don't know. Anyway, you get the idea. Oh, and someone just dropped a video. That's great. That's going to go ahead and now we're going to have 25 people downloading an MP4 file over the Wi-Fi. That's really going to help. Thank you. Thank you for that. All right. Anyway. Okay, let's keep going. So, okay, third thing let's do. Let's build a chat app. So the WebTorrent stuff is pretty easy because the API makes it simple, but let's say we want to build something a little bit more complicated. So a chat app. So something like, think like Slack, but peer-to-peer. So I have to explain one thing first before we go further. I have to explain how you connect two WebRTC peers to each other, at least at a high level, so that we can go forward. So first, let's remember how TCP connections work. So if you want to connect to a computer on the network using a TCP, all you do is, if you know the IP address, you just connect to it. Now, obviously, more things are going on under the hood, but from an API perspective, you just say connect to that IP, and then you're connected. You get a stream back that you can use to communicate with that endpoint. WebRTC is a little bit more complicated. So part of the reason for that is that, actually, give me a sec. I want to do something here really quick. Is that good? Okay, yeah. So we're running JavaScript in a browser, so we don't want to like have JavaScript that's running in an ad, for example, connecting to your printer in your house and printing things. That would be really bad. So we need a little bit more sanity around how the connections happen, and we also need to, ideally, we will do things that are nice for 2017, like for example, let's encrypt all of our connections by default, and while we're at that, let's maybe throw in some NAT hole punching, which is a thing that you would want in any peer-to-peer application. You want to be able to ensure people behind NATs, which is basically people behind any Wi-Fi router, can connect to people and punch through that NAT. And so you can really connect to the person even though they have a private IP address which isn't even routable on the internet. And so for all these reasons, we have this WebRTC handshake process. So the way it works is you say, I want to connect to somebody, the browser generates you this offer, which is basically a description of your IP address, your encryption keys, and some other stuff, and it's a blob of text. And then you have to give it to the person who wants to connect to you. You do it through however way you want. And probably it's going to be a central server. So you get them that text, and then they produce an answer which contains the same information but from their end, and they get that back to you. And then when you both have those blobs of text, then at some point you just connect to each other, and the browser just takes care of it. I don't have time to get into more detail now. Just let's just go with this for now. So, so I will say the connection process did involve us going through a central server, but eventually we got this connection which is peer-to-peer, which is a browser connected to a browser. So we have a module that makes this process a lot more sane, and it's called Simple Peer. So you can require Simple Peer, say you want to make a peer, and this is the part where you say, I want to connect to somebody, right? And so at some point, the browser generates this signal event, which is going to give you this blob of data that describes how to connect to you, how to connect to this browser. And so when you get that, your job is to send it to the peer that you want to connect to, the remote peer, via some mechanism, probably going to be a central server, like a WebSocket server or something. And then at the same time, you have to receive the message that's going to come back from that peer via some mechanism. And when you get it, you call the signal method on the peer object. And so it's parallel, right? So as long as you hook this up like this, at some point you'll get a connect event for the peer, and the peers will, on both ends, will be connected to each other. At which point you can send data. And then you can listen for data on that peer-to-peer connection just like that. And so we're starting to have the pieces that we need to build this decentralized chat application. But we're still missing a few things. So we need to figure out how peers are going to find each other. And so for that, we're going to go back to our old trusty Signal Hub, and we're going to broadcast a hello message when we first load up the app, so that we're basically announcing to everyone who is in this chat room that we're here, hello, And when we do that, we also want to give them a way to identify us. So we create a local peer ID, which is just a random string. And whenever someone gets a hello message, they're going to initiate this simple peer process. So they're going to create a peer, then listen for the signal event, and when they get a signal event, broadcast it. But they're going to broadcast it just to the peer that they want to connect to, not to everybody, right? Because they got a hello from one person, and they're trying to connect to that person. So when they get that hello, they broadcast not to the hello channel, but to a channel that's named peer ID. Excuse me. So every peer listens on a channel, subscribes to a channel that is their own peer ID. And so in that way, we've hooked up the signal events to each other so that the peers can connect. And the last thing we need to do is, when we actually get data over the peer-to-peer connection, we will push it into a little store that we're going to use. It's like Redux type app that we've built here. So we push it into our store, and then we update the UI. And then to send a message, when the user types into the input box and hits send, we essentially just produce a little message object that describes the text of our message and who it's from, and then we iterate over all the peers that we're connected to and send them the message. So we have to be connected to basically everybody who we're chatting with in the room, and have an active connection to each of them in order for this to work. Okay, so now we're going to see how this looks. So I'm going to go to the server and change folders, run a new app. So if you still have your laptop out, go back to Nordic.js.fun and refresh. And now the app has changed. So it's going to ask you, it might not work on phones. I haven't tested it on mobile browsers, so just beware. So it's going to ask us for our name and an email address so that we can have a Gravatar image come up. This is not required, but I just think it's cool. So cool, we're connected to this chat room. We have tons of people connected. Nice, messages are coming in. Cool. Thanks. I can't believe the number of peers. Do we really have 80 people all doing this? That's pretty incredible. Cool, so that's that. Just like that, we have an app working. Okay, last demo, let's see, well, we have time. So, let's find out how performant WebRTC data channel actually is. Let's build a real-time game. Okay, so I'm gonna gloss over this a little bit. This is just, we're gonna listen to a bunch of keys, up arrow, down arrow, left arrow, right arrow, and then we're gonna set some state. When a peer contacts us, we're going to get from them a position, an XY position, and a velocity. So this game is going to involve players moving themselves around a screen, a 2D world. And so the peer is basically going to send us their location and their velocity on regular intervals. Now, why do we need to know their velocity? They could just tell us their position, right? Well, the thing is, we don't want to have them sending us so much data that it's going to overwhelm our connection. So what we do is we have them send us their velocity, and then even if we don't hear from them for a while, we can actually just extrapolate and run at 60 frames per second and push the peer along in the direction that they were going before, which most of the time is the direction they're going to continue going. So it'll work out nicely. And then once every 100 milliseconds, we send out to all the peers our current position so that they know where we are. And so this is going to be an object that just contains the same thing as x, y, velocity x, and velocity y. And to send all, it's simple, the same thing we did before. It's the looping over all the peers and then sending our position to them. And this is our tick method, which is going to be run 60 times a second, where we basically just adjust the player's velocity depending on the key that they have down, and then we also adjust our position based on the direction we're going, and then we also move all the peers by the velocities that they're going. So we have basically everyone moves, and then we call update, which actually renders it to the page. And we're using a React type thing for this, so we'll see if it's a good idea to have that many players all being DOM nodes and stuff. We'll see if it performs. Okay, so let's do it. Uh-oh. I lost my SSH connection. Close your browsers, people. For a minute, just for a minute. Oh no. Okay. Okay, we're good. Yes, all right. See if it, some of you are connected, I hear the sound. Let's see if I can get it going so that, let's give this one more try. So those of you who can see the game already know what's going on, but okay, there we go. Okay, my image is, okay, so the idea is you go after these little disks, and then we're supposed to see other peers show up. I think my internet might not be good enough. Let me try refreshing. Okay, there you go, that loaded at least. Will we get some peers? No. Okay, so something's going on. Oh, there we go, there's a peer. So I think there's something going, oh, you know what it is? I think the remote images aren't loading for the other peers. So we're just getting like invisible people taking the disks. Oh well, fair enough. Well, okay. We'll try it later, I guess. Anyway, oh, let me turn the sound off. Okay, so I'll just close on a few final points. So peer-to-peer has a lot of challenges because topologies are more complex in peer-to-peer apps. You have to think about sort of how you want to connect peers to each other. So in these examples, we were just naively connecting to everybody, which clearly doesn't scale in this situation. Also, you have trust is harder. So in the code we wrote, we were just having every peer announce their position to the entire network, and people were just trusting it. So that wouldn't work in a real game where you want to worry about cheaters. And the architecture is just more complicated, and there's also fewer frameworks and less starter code. But there are some things going for it. So one is it's cool. Two is we can actually reduce costs for hosting in the case of like the torrent examples. And oftentimes with peer-to-peer apps, you get offline support automatically. Because we're not relying on URLs to tell us where to go get something, we don't need to go and check it as often. We can just get it once and then cache it forever because it doesn't change. We use content addressing, which is basically describing the content by itself via a hash. And oftentimes you can do privacy by design and do things like push data and control as much as possible to the endpoint so that the user is in control of their data. So there are some solutions to the challenges that we talked about for peer-to-peer apps. And so there's some work that you should look at if you're interested. Look at the work by Macintosh, Tara, Vansil, P. Frazee, Diaz David, Dominic, and Andre Staltz. And also take a look at Beaker Browser, which I think is really impressive. And thanks for listening.
Thank you so much.
Thank you.